focusing on quantum. And I know people are pretty active in Zoom calls. Feel free to message, chat your questions or comments and anything that you want to learn more about. Feel free as I talk to post in the chat box. I will try to look at it. And can everyone see my screen now?
I can see it, and I bet
right.
everybody else can see this one.
Perfect. Thank you so much. Okay. Get to it. Great. Just a little bit of background about myself, as Farah already mentioned some things that I do physics and art at the same time. If you look at my professional track, I've always been working on fundamental condensed matter physics, and then went to applied physics, and now I work at Microsoft for doing quantum computing and being one of the senior program managers, and I'm driving several projects in the team. That's my day job and that's my passion, but I also have another passion, which is art. So I've always been doing these in parallel, merging technology with art, expressing technology with art. So I have my own fashion brand, and I also have a fashion tech projects that I'm leading at Microsoft. So they are seemingly two parallel tracks, but they have been integrating in my experience the whole time. My background was in hardware. I started my professional career in condensed matter physics, and I actually worked on the dilution refrigerators that's needed for several types of quantum architecture. But when I was working on it, there wasn't really a quantum computing industry. So we were doing more fundamental research. And I actually built parts of the dilution refrigerators, things that can help the fridge cool down to really, really low temperature. That's my background, but I started learning programming on the side, and quantum computing as the programming computing area was something that I picked up in industry while I was working. And at Microsoft, we have the Q# language. We have also developed our own hardware and compiler and everything, the whole stack. So I actually started learning quantum computing just as everyone else. I'm curious to see what background people come from. So feel free to type in where you're from, what's your professional background, why you're interested in quantum. And I'm curious to see if you are already working in quantum computing or you're learning that. So in terms of the hardware, that I have professional training in physics, but then there were so much new things to learn in industry. So I actually picked up the software side and learned about the quantum computing as an industry while I'm actually working on something different. So today I'll be showing you my project, delivering a conceptual talk about quantum computing and using my art that merges science, engineering, design, and art together. That's my way of expressing, and I do all my projects. I try to merge all of these things together. So you will be seeing me presenting quantum computing using comics. And that's something that I actually developed as I was a student learning, which is to try to use 3 different ways to express the same thing. And by doing that, I can find the point where I actually understand it. So if I can describe something with words or equations, but if I cannot draw it, that actually shows that I don't actually understand it. So this is something you may like to try. That's also how I make sure what I'm learning in quantum computing it is correct. So I check it by doing all these different things merging. Coding is definitely now a accessible way to make things more concrete and practical. Have people worked on any quantum languages or tried any of the industry products? I would love to hear your experience. So today's talk may be familiar, the concept may be familiar to some of you if you have already done some learning of quantum computing, but I hope that still I can bring something interesting, different to help or get you further interested in this area. So take a step back and think about where we are. We're living in this world of technology, and everything is connected by internet. The reason we can talk to each other right now is because we have all the infrastructure built to connect everyone and all the things together. We also know that there are still certain tasks that are still very difficult to do on traditional classical computers. Things that are fundamentally quantum mechanical or very complex problems that we can get inspired by using some quantum methods. And they made things like signal processing, information security, logistics. We can also, they're not quantum mechanical, but we can use quantum methods to help solve. And quantum computing really is a way we are engineering to help us achieve certain difficult tasks by copying and emulating nature, just like many other engineering work that we are learning from nature and we are imitating it. I call it biomimicking. Just quantum computing is like biomimicking. And that is how our fundamental building blocks in this world is built onto fundamental particles that behave in the quantum mechanical, subject to quantum mechanical laws. And then we are using some phenomena to build computing that can help us do algorithms, solve problems differently. If you look at the landscape for a learner, you would need to have certain understanding in the concepts and also a little bit of math, a little bit of linear algebra, but it's not very difficult. You can just understand the methods that's used for the gates and constructing quantum circuits, and very quickly use computing language such as Q# to write algorithms and run on hardware through the cloud now. So you can do all of these. So to start with, I would walk you through some concepts and then guide you towards more learning materials that you can learn further. I will describe quickly some of the famous algorithms. We have learning materials to support all of these areas. If you need, just find them anytime on the Microsoft websites. We have documentation, MS Learn, code samples, katas as an exercise for learning Q#. And of course, we have UnQuantum. Now you can use to access all kinds of hardware, quantum hardware through the cloud. I can post these links. Oh, maybe I cannot do that while I'm presenting, but I can share the links later in the chat or give this slide to OneQuantum. All right, let's get started. So for some of you, this may be already familiar, but I hope that the comics is still interesting to see. We know that we are describing information using the binary 0 and 1s. And in computing hardware, it is just like little switches using transistors to achieve those 0s and 1s. There are many ways to represent information, but when it comes down to computation, that's how we are representing information. That the information can be represented as states, classical. So if we look at classical bits, we just have 0 and 1, and we can use a vector to describe the two states. These are conveniently chosen as examples of two options. So you can use binary numbers to represent them. And in hardware, you would just achieve it through transistors. If you have electricity through source to drain, maybe you can call it a 1. If there's no electricity through the transistor, then you can call it a 0. It's a very high level understanding of that. So this is how we do classical computing. But then that is such a simplified version of how nature behaves, just having two options, two states. We know in our nature's building blocks, like electrons, photons, or atoms, we can find energy levels of these particles. And say electron in the atom, they can have different energy levels they can sit on, and they can be in superposition. The electron can appear at any level at any time. So the superposition is the first concept from physics that we're using in making quantum computing work. And what is superposition? If you compare it to classical bits, you see that you can have examples of, say, I draw a circle. If it's 0, if it's filled, not filled, empty, I can just say, oh, this information is 0. If it is filled, I can use a 1 to represent it. Or if you have a lottery bowl, you have the beads. If all of them are red, you can call it a 0. If all of them are blue, you can call it a 1. Or a coin that you can label 0 and 1 for the head and tail. But then if you had a quantum bit, the information can be represented with the probability. Like similarly in these examples, you can have 1/3 of having a 0 and 2/3 of having a 1. Or you can have 8 beads that are red and 12 beads that are blue. And a spinning coin, if it is a fair coin, you can have half probability of landing on 0 and 1. So you can see that quantum bits can embody probability of 0 and 1 of the two possible states. That's for 1 qubit. You know that you can write them mathematically as superposition, which is a linear combination of 0 and 1, and you have certain weights, A and B. These are just coefficients you use to say how much of 0 or how much of 1 is in my system. They can be any number. You just have to make sure that the probability add up to 1. And A and B are amplitudes. Amplitude square are probabilities. If you have 2 qubits, then there are 4 possible configurations. If you have 3 qubits, there are 8 possible configurations. So you can see that the number of possible configurations grow with 2 to the n if you have n qubits. And that's not just it. It grows exponentially, but also every possibility has an amplitude in front of it. So you can have infinite possibility, infinite types of amplitudes in front of your state, your configuration, to form the overall system, all in superposition. These amplitudes can be any number. It could be positive, could be negative, could be complex numbers. So the possibility for a quantum system to represent something is not possible for classical bits. You're not able to find any put any classical bits together in the same way to represent the same information that quantum computing can do. So this is the very first misconception that one may have. Maybe you heard from popular media that perhaps, Brian, I think you are not muted, so we're hearing noise. Would you mind muting? Thank you. So this is misconception number one, where you may heard from some sources that people like to say a qubit is 0 and 1 at the same time. That's not a very good description. What does it even mean? And there's no concept like time here either. Time is a very specific physical concept. What it really means is that there's a linear combination of two possible states that you can get the probability of having either of them. That is what a qubit can represent. And then the second important concept from physics we use in quantum computing is interference. Interference, you might have heard, you have seen in everyday experience, waves. Those are waves that have amplitudes, and they can have positive addition, they have constructive interference when their phases are in line, and they can have destructive interference if their phases are out of sync and they cancel each other. This happens in a quantum system because every state, as I showed earlier, has an amplitude associated with it. So that means the states can interfere with each other. What does it do? In classical system, if you want to calculate a probability, say we have a simple example, you want to predict if the day after tomorrow is sunny or not. And you can either have sunny day or rainy day. And you write out, you can just like what we learned in primary school, maybe as kids, draw out all the possibilities. And in classical situation, you get all the probabilities and you use the probability to calculate if the day after tomorrow is sunny, you find, oh, there are two possible paths to lead to sunny days, and you time the probability and add them up. So in this case, fictitious numbers, you get 60% possible. But then in the quantum system, as I mentioned, amplitude can be anything. It could be complex numbers, it could even be negative numbers. And in quantum system, we don't directly use probability anymore. We need to use amplitudes. And there's nothing stopping me from putting a negative sign in front of one of the amplitudes, just to prove the point, where when you have this negative sign here, it destructively interferes with your other possible paths. And turn out, even with two paths that can lead to sunny days, it could even reduce your chance of having a sunny day. So in this example, we only get 8%. This is the interesting thing about quantum systems, is that you can have interference between possible paths, and that could be very, very useful in algorithms, which I will show you in a bit. Interference is not something that's just we're not able to observe. Is a very direct phenomenon that we can even see in experiments. You may have heard of the double slit experiment, where you could have a beam of electrons, they are all quantum particles. You have two slits, but if you block one of them, you have the most possible point of getting most electrons right behind the open slit. And classically, you may think that, oh, if I open the other slit, you will get two peaks, but that's not what we observe. We see interference patterns. That is a manifestation of quantum interference right here. You can even have the peak right behind the barrier. And behind the slits, you could even have destructive interference where you have very low probability of having the electrons there. So interference is very important. I think it hasn't been talked very much in quantum computing fundamentals. And this is one of the key phenomena that we use in algorithm. And a quick note about measurement. This is a measurement when we observe directly the interference. And measurement is nothing but finding out the amplitude and the probability of having a certain state. And it's not reversible. So in the analogy of a spinning coin, you don't know which side it's going to land on because it's both possible. But then if you knock it off, if you knock it down, then it's action of measurement.
Number one.
Hi, Gil. Billy, can you mute yourself? Thanks. So this is not reversible. You get one outcome, and that's what measurements behaves, it manifests. If you have a quantum state, say you have 2 qubits, you have 4 possibilities, and each of them has an amplitude in front of them. The probability, so say if you do one measurement and you find out the first qubit is 0, then from the states of these 4 initial states, you know if the first one is 0, it's not possible that these 2 is from these 2. It must be from these 2 states. Then you know the probability of getting the first qubit to be 0 is these 2 amplitude squared add up. And then after measurement, because you know the is not contributed from these 2 states, you know after measurement, your system only has these 2 states left. And the square root of P under here is to make sure, again, the normalization condition I mentioned, that in any complete system, you need to have the amplitude square add up to 1. So this is just to normalize it. So this is what happens when you do a measurement to a quantum system. I think if you have taken any physics, quantum mechanics classes in the past decade or more, you may have heard the textbook like to say the collapse is the Copenhagen interpretation of measurement, what happens at measurements. All the wave functions would collapse into one when you do a measurement. But if we look at the previous examples and look at amplitude, it's not really, collapsing doesn't really explain anything. It is actually when you do measurement, what you're getting is the most possible outcome, because the other less possible outcome gets destructively interfered. So you get you don't measure those. That's why that's what's happening when you do measurement. You are actually measuring the most possible states that was in your system. So this is the number 2 misconception here. And then the third important concept is entanglement. You might have also heard a lot about this in popular science. Entanglement, what a mysterious thing. When you have 2 qubits entangled with each other, you can separate them even far apart, but they stay entangled. What does entanglement mean? It's nothing but putting the qubits into certain configuration that they are inseparable. They are special configurations, for example, that can be put into superposition. For example, there's nothing stopping you from, if you have 2 qubits, there's nothing stopping you from putting them into a 0, 0 plus 1, 1 state, or a 0, 1 plus 1, 0 state. And what happens then is that if you measure your first qubit, if it turned out to be 0, you know it's from this state. So your second qubit must be 0. Or if you measure your first qubit and you get a 1, you know it's not from this state. It's not from this this state is from this state. So you know is the second qubit is 1. So you know that information even without having to measure your second qubit. There's nothing mysterious. There's no spooky interaction. That's a really misused phrase. That was back when physicists, when they first discovered quantum phenomena, they didn't quite know what's happening. So they were trying to understand it. And the spooky interaction between two entangled pair at a distance is a very misleading phrase. So don't be fooled by that. There's nothing about changing one qubit, the other one will immediately also change. And that's a big misconception about entanglement, is that they are entangled, so you cannot separate them. You cannot represent them separately into two separate qubits anymore once they're entangled. And when you change one of them, it doesn't mean the other one automatically also changes. The other one doesn't. You just know what the other one would be when you measure one of them. So let's take a look at this example. So these are Bell states, which are special states when you have the amplitude of these two states in superposition having the same amplitude in front of them. So square root of 2. So you know this is normalized. Their probability add up to 1. Let's use this state as an example. I mentioned already that if you measure 1 and the first qubit and it turned out to be 0, you know your second qubit is a 0 with a probability of a half. Similarly with the other state. And if you can entangle 2 qubits, there's nothing stopping you from entangling multiple qubits. And 2 people can use this as a way to achieve communication. So when you entangle a pair, you can have one person keep one of the qubit and the other one go whatever they want far away. They know what the other person will get once they do a measurement. So you can use this in encryption or communication. And entanglement can be very useful, and all of our quantum algorithms will use it. I'll show you in a reverse example. But it can also be dangerous. We don't want unwanted entanglement in our system. For example, if you don't isolate your quantum system well, your qubits might as well entangle with your environment or get entangled with your actual measurement probe, because at the microscopic level, they're all quantum particles. And that can cause decoherence, and you disturb the system, and then you would not be able to use your system the way you want. So entanglement can also cause decoherence. So now these are the 3 common misconceptions in a nutshell. Is qubits are not 0 and 1 at the same time. Measurement is not wave function collapsing, and entanglement is not spooky interaction at a distance. Changing one would change the other one instantaneously. So that's the concept, the 3 concepts that we need for establishing quantum computing algorithms. All of the algorithms like Deutsch-Holzer, Shor's algorithm, Grover's algorithm, they all use interference and entanglement. And both interference and entanglement are enabled by the fact you can put states in superposition. So I hope that was helpful. Now we'll move on to an example to look at how does a algorithm use interference and entanglement. Just a brief overview of historic development. a lot of our current algorithms are based on some textbook algorithms developed by Shor and Grover. And we have a pretty brief history in quantum computing, and especially in the past 20 years or so, a lot of the development has been done on the algorithms. And today, the hardware still needs to catch up to be able to carry out these algorithms. And we think that there are 50 more quantum algorithms that can bring quantum speed up. This is an active area of research. There are many application areas that we think it may be possible to use quantum computing for, but we don't currently have the hardware to be able to run those yet. That's why we really need people to join forces to develop algorithms as well as the hardware to push this industry forward. But I will show you an example to see how quantum algorithm can bring speed up in a concrete example. This is the quantum algorithm zoo that is maintained by my colleague Stephen Jordan in Microsoft. So feel free to look it up. There are loads of them, but they are also grouped together into common themes. Okay. Very, very quickly, I don't know if people have in the audience have already done algorithm. I don't want to overwhelm you with too much information in one talk. But at a high level, I want to mention that if you want to build algorithms, one of the ways to represent them is to use a visual representation. These are gates. You probably have seen these written like lines and boxes. So a line is a qubit, and we use the boxes to label different gates to apply onto these qubits. And what are gates? Gates are just matrices, because I mentioned it very early. You can represent states using a vector, and a quantum bit can be represented by a vector. And how do you manipulate vectors? Just use matrices, apply this mathematically, and that can change. That's an operation that can change your state. And in general, you can write out for single qubits, you have generally these gates, these matrices that can change any arbitrary vector. And if you want to represent an arbitrary vector, that is a 3D space where you can have any point on a sphere, and that you can graphically represent as a qubit. But that's a single qubit. You might have heard of the term block sphere. That is mathematically you can represent a vector onto a point of a sphere. But we're not going to go into detail today. That's probably going to take up too much time, but very high level, if you want to change one qubit, you use matrices, and these are, why do they have angles on them? Is because if you represent the vector onto a sphere, by changing them, you are effectively changing the angles of where your vector is pointing. So the arbitrary matrices that can change angles are these two. But there are most commonly used gates that you can plug into the angles here and get those like X gates, Z gate, Y gates. Those are specific gates that are mostly commonly used. And then if you need to have multiple qubits and then have them interact with each other, you would need to have control gates. For example, the control NOT gate is a 4x4 matrix. As you see, for a vector, a single qubit would be only a 1x2 vector. and you only need 2 by 2 matrices. But then for more qubits, you are expanding the dimension, and you can no longer represent them using a block sphere, because we can't really draw up to 3 dimensions. And control matrix would be able to allow you to manipulate multiple qubits. For example, here, this is a gate that allows you to modify your target qubit, which is the second qubit, based on the state of your first qubit. For example, if your first qubit is a 0, you see that the second qubit doesn't change after applying this matrix. But then if it is a 1, they flip from 0 to 1. So definitely try the math yourself afterwards. Okay, let's go forward to an algorithm. I know jumping to algorithm would be quite a few lectures ahead, but I want to give people some high level idea on how to view algorithms. Grover's algorithm is a nice one. I like to use for classes like this because it's not as simple as Deutsch-Hose algorithm, which is a nice textbook algorithm, but it's not very useful. Grover's is actually a useful one. And there's Shor's algorithm, but it's a little too complex to talk about in the very first class, but I will mention it later. Grover's algorithm in a nutshell is a good algorithm for searching. Give you an analogy. If you go into a library of books, you know a book title that you want to find, but unfortunately this library is very messy, is very randomly arranged. You don't have an order. Then how do you find the book that you want? Classically, if you use a classical algorithm, you have to look at them one by one, until you find it. If you're unlucky, the very last book is the one you're looking for. But then if you can use Grover's search algorithm, you can put all the book title into your algorithm, and they would do interference. The unlikely titles would destructively interfere with each other. And the likely title, the one you're looking for, will gradually get higher and higher amplitude. And when you do measurement once, you get that book out. So these are the scaling factors. These are how the algorithms run efficiently with the number of qubits. So classical algorithm, if you do the one by one, looking at your the book title, if you have n qubits, it scales as 2 to the n. But for Grover's algorithm, it scales as 2 to the n over 2. So you can see that maybe at the beginning, when the qubits or bits numbers are not very big, we don't have an advantage using quantum algorithm. But at a certain point, Grover's algorithm is going to win. It would be much more efficient to use a Grover's algorithm when the number of qubits are large. And how large is it? Our current estimate is like millions of qubits, including error correction qubit, because I mentioned the measurement has to be very delicately done, and you need to, the quantum system can have unwanted errors, and you have to correct them with extra qubits. So in order to run some useful algorithm like Grover's, it would need so many qubits, and we don't have any quantum computer that can do that. It's going to be a constant race between classical, the fastest supercomputer, and the fastest quantum computer. At some point, we hope that we will be able to get to a point that quantum computer can clearly show the advantage. And one active area of development in quantum computing is to find more algorithms at lower, that need fewer numbers of qubits that can still prove to be useful, while we develop hardware that can allow us to have more and more qubits. So that's the state of our quantum computing industry, developing algorithms using fewer and fewer qubits that can be useful, and developing hardware. Both are ongoing and they help each other. A quick note that in quantum algorithms, we use something called oracle. Those are boxes that you have to conceal, and you allow the entanglement and interference to happen within the oracle. And what it does is to make sure that your algorithm, your operation is reversible. And that's required for a quantum operation. And I didn't mention earlier that a quantum gate is also reversible. So it makes sense, because if you think about your system, you do an operation, but then you do want to reverse it back, which is different from doing a measurement. Is not reversible. Once you do a measurement, things becomes a classical information. That's just some details there. So I will not go through the math here. This is to show that when you have an algorithm, you need to build oracles to make sure that the operation is reversible, and an oracle allows you to do that. Let's take a look at the Grover's algorithm step by step. What's happening is, if you establish a Grover's algorithm circuit, so a circuit is a visualization that helps you imagine what happens. But in the real useful case, it will have so many qubits, you will not be able to really draw circuits. Right now, just for the sake of proof of concept, we only draw 3 qubits here. So you have 3 states in your system. At the beginning, you initialize all of your qubits to be 1. So you have this 1 state to have a 1 amplitude equal to 1. And then what the H gates do is to make a superposition of all of the states, so they have equal amplitudes. And then what this oracle box does is labeling. It uses I will show you in a bit. It labels the state that you want to label, you want to find, like your book title, by making it negative, and all the rest are positive. And then you do some mathematical trick in this box, allowing it to flip around a mean of all the amplitudes. So you see that this one gets flipped to a higher amplitude, and the other ones reduce amplitudes. And then you repeat this not couple of times, there's a number of times. Repeat, if you have n qubits, you repeat square root of 2 to the n times. And then when you do a measurement, this labeled amplitude becomes the most likely result of your measurement. That's how Grover's algorithm works. If you look at the specific circuits step by step, they involve the control gates, and they involve the X gates, H gates. So this is to mathematically set up the oracle step by step. I don't know people's background here, if you already have done algorithms and you know what the gates are. So I'm here kind of assuming that you do know. So they are matrices that controls your target bits using these input control bits. And then let me just skip this. You can set up your algorithms based on which one you want to label. So they would just be expressed by where you put your X gates in the oracle. And in this oracle, we have an example, which is a 111. So you're labeling 111. And this gate would do that. And I've mentioned the initial part is to have the amplitude equalized using the H gates. And then the very last box is allowing you to do a phase flip. And what it's doing here is very similar to this oracle box here, where you have the amplitudes of all of your states, but then give a negative sign to one of them, and then you flip it to have this one to be positive and all the rest negative. So you see, there's a lot of details here. I'm not covering. If you're interested, you can look up on my previous talks. I'll give you the link later. That actually we do the Q# programming step by step, so you can follow this while you do the exercise. But I'm just going through this very quickly just to show you that all these algorithms, these boxes do, are manipulating the amplitudes of your states. So then at the very end, we have these gates that would do the mean, the flip of the amplitudes around the mean amplitude. And that's what's making your labeled amplitude to be larger and larger, and the other ones reducing. So I'm not going through the details, but just showing you that all these oracle boxes do is to allowing you to enter, to have a interference between the amplitudes and giving them negative signs to label them. And of course, the qubits are entangled. And how do we know how many times to repeat this algorithm? There's also a way you can calculate, you can map the amplitude onto a vector space where you have the angles to, you can draw them in just a 2D space to find the state in your system. And these repeated steps one by one is allowing you to start from this state and gradually move your state over to the final state that you labeled it. So I think this might be a little bit too crunched up for one class, but if you want to follow through the details, we have several classes already on Grover's algorithm in my past lectures. You can look them up, and in which I would explain the details. But I wanted to give you a high-level view that's how a quantum algorithms works. And similarly, for Shor's algorithm, you also are manipulating the amplitudes. In Shor's algorithm, you are effectively finding the period of the system. And what you input is a set of amplitudes, but then they're put into a periodic state. And what the Shor's algorithm does is doing a quantum Fourier transform that allows you to find the period in your system very efficiently. And that period there is what's used in encryption, like RSA methods. And that's the secret that we need to keep for the encryption. So yeah, let me not go into the detail of this, but I will jump to the other aspects. I showed the algorithms in terms of circuits, but I already mentioned they can get very messy if you had too many qubits, because in order to have useful quantum algorithms, you do need lots of qubits. So using circuits to draw them out is not scalable. That's why we need languages. That's why Microsoft developed our Q# language to be able to just write a few lines of code to capture a lot of the steps in a algorithm. And then finally, hardware. We have currently many different types of architecture. And I mentioned the transistors are used for classical. In quantum qubits, we are exploring many different types of systems. In research, there were a lot of work done using like 2D electron gas and form quantum dots. You can trap electron into your little region and use electron spin, or you can use a crystal lattice and have electrons trapped in a vacancy, and you can use that electron spin to represent your qubit zeros and ones. But over time, the industry finds there are better ways to do things and more scalable. So a lot of the companies are now using like trap irons and superconducting circuits. So trap irons are the ones, instead of using electron traps, you have iron traps. You can isolate ions in electromagnetic fields and also manipulating their spin to represent your zeros and ones. And the superconducting qubits are kind of the artificial atoms where you can form a resonance between your circuit components. This is, if you have done electrical engineering, you know, if you have a capacitor and inductor LC circuit, that can form a resonance. But in the superconducting qubit, you need a superconducting inductor made using Josephson junction. What it does is to allow you to form a resonance, but also having the energy levels to have different spacing. And then you can pick two of the levels to be your zeros and ones. You don't have to limit your imagination to energy levels to represent your zeros and ones. You could also have like photonic qubits where you can have different polarization of light to be your zeros and ones. And of course, you might have heard Microsoft is pursuing very different methods using topological circuits. Those form special states for electrons to occupy or unoccupy. And those can also be used as your zeros and ones. So for hardware, at the lowest level, if you want to make qubits, you have to basically have certain representations of zeros and ones depending on your hardware architecture. So of course, the hardware is an ongoing area of research, and right now is still difficult to say which one would scale, which one we know theoretically the most scalable way, but technically very challenging. So all of these architectures are being developed at the moment. So will be very exciting next few years. Okay, so that's the core concepts that I wanted to show. I know it's a very short talk for a lot of materials. Don't worry if there are things that are not immediately clear. We have a lot of learning materials for you to look into. So at least I hope that this class can allow you to get interested in quantum computing. We have this website called the Quantum Learning site, which is on azure.com/quantum.learn. It actually gives you a personalized learning path when you put in your background and your interests. This is a nice 3D representation of a qubit, but it also represents your answer, why you put in answer these questions. And then you will get recommended learning materials catered to your interests and background. And one of the materials I want to highlight is the MS learning courses. So here's a short link, aka.ms/learn quantum computing. Those are step-by-step guides for you to get immediately hands-on with quantum algorithms, learning Q#, and also the concepts of quantum computing. We have a series of materials from the very fundamental all the way to leading you to running algorithms on Azure Quantum and using different types of hardware. And here is a summary page of all of the useful links. I would copy and paste these in the chats and also share this with Farah. Maybe he has a way to share the slides with you. And furthermore, if you want to use the comics as a guide, I did give a class at Hackaday U last year. Every Sunday I was given a class, and it was 30 minutes to an hour on one single concept. So if you find today's material too dense, too much, we have broken that down into short lectures where you can follow step by step. And we use the quantum documentation and the katas as our exercise. And then finally, all these comics, I actually was able to draw so many of them, and they accumulated into a book. I don't know if you are able to get them in your area, in your region, but these are available in hard copies. So if you're interested, search on your Amazon site the code here and see if it's available in your region. So that's it. Thank you so much for joining. We're a little bit over time, but I hope this was useful.
Thank you very much, Kitty. I really appreciate your time. Beautiful presentation and a lot of interesting comments about your work, and obviously a number of questions as well in the chat box. Let me see how this works. Just trying to see if my video feed can work. So what we're going to do is we're going to turn your, perhaps request that you turn your attention to the chat, and we will pick some questions that have been coming through during your presentation.
Thank you.
So let me see where that happens. What could have been our first question? Okay, let me just roll through the chat and bring that to you. So Nyameko says, I love your sketch notes. Animations and graphics are truly one of the best ways of teaching concepts at all levels, as it engages both hemispheres of the brain and reinforces the neuron connections amongst associated ideas. Any chance you were inspired by Sasha Chua and her blog, or Mike Rhodes and his sketch noting handbook, or similar vloggers like Paperless X, etc.? Moreover, who, if anything, sketchnoting YouTuber blogger do you follow? Then I think you can turn to the chat so that I don't read and repeat, and you get to make a sense of them.
I'm trying to find the one you're reading. There are a lot.
It's actually at the very top after people's introductions. So what will be the timestamp for that? I don't have it actually. So you just try to scroll to the top and you'll see one very long one, and then we'll start from there going down.
Yeah, from Nyameko, Lisa? From
Nyameko, yes.
Yeah, thank you so much. Yeah, the graphic novels are pretty much a way for me to express ideas. I have been doing making comics books and comic stories since I was a child, and this is definitely a way for me to also test my understanding. If I can draw it, that means I understand it. If I can't draw it, that means I really need to study more. So this was also a learning experience for me to really be able to express all these with drawings. I haven't read Sasha Chua's work. I actually really liked Lara König, who's a very famous comic book, sci-fi, and history cartoonist. I read his work when I was young, and I was very inspired by it. So I will look up on the ones you mentioned here. Will be very interesting to see. What do I use to create? I use Photoshop and Adobe Illustrator. As Farah also mentioned, I do fashion design, and I also use these, Adobe Illustrator and Photoshop for all of my graphic novel and fashion design. All of my fabrics are my own paintings printed on the fabric. So these are my favorite tools. I do directly digital design on my computer. And there's a third question. If you use this technique to take notes during lecture, I did. Yeah, it's a great question. I didn't do this much when I was a student, but then I converted those into graphics when I was studying myself. During lectures, I started doing that. I kind of trained because it really requires speed drawing. And this is something that I want to train myself to do. So I did a few before. But I'm not, I'm really I really admire those people who can just draw right as someone talks. I think this is an amazing skill that I'm training myself to do, but I'm not giving myself too much pressure.
Sounds good. You can keep scrolling, going down.
Okay. Yeah, thank you for your nice comments about comics. So Def dot asks if there's no remote connections between two qubits more than c. I don't know what, speed of light, due to upper limits of speed of light. Yeah, why we found violation of Bell inequality again and again. What is the physical cause behind? I haven't understood it completely. So I think I have to look it up myself and make sure that I can draw it out to be able to explain it. But there's no violation of speed of light. For example, in teleportation algorithm, you are sending information through your entangled qubits, but you're still doing measurement on your system, and you need classical methods to communicate, and there's no violation. There's no speed of light faster than speed of light information transfer.
Excuse me.
Yeah, you wanted to.
Yes, ma'am. Yes, ma'am. Actually, I want to ask that there is a Bell violation again and again. Bell inequality violation.
I have to look up on the specific examples. I don't.
Yes.
Yeah, I don't have enough knowledge to.
They are
really
or reaching two qubits are correlated. Yes.
Sorry. Yeah.
Bell violation. The distance qubit are correlated by the Bell violation, Bell inequality violation. Means what is the reason behind this Bell violation?
Let me look it up and try to find some research papers that does the measurement. So I don't quite know how to answer it right now.
Yes, okay. Thank you.
Yeah, thank you. Is it possible to interface the Microsoft quantum machines using Visual Studio? Yes. We do use Visual Studio and Visual Studio Code to directly access the hardware, and that's one of the development IDE. You can use other as well, but if you go to the Microsoft quantum documentation and or the MS Learn courses, you'll be able to find the instructions on how to do that. Let me post the links here so you can try those things out in your own time. Oops, I think that says direct message. Let me see, what else do we have? All right, yeah, thank you everyone.
So we've got one that came just now on the chat from Abdul. In your opinion, what are the most effective techniques that you may use for your deep quantum workshops? Like how to interpret your talks for higher educational levels?
Yeah, so I think quantum computing is such a big area, and there's also the touch of quantum mechanics, which goes much deeper. It is a difficult balance between how deep you want to go, depending on your audience. So I didn't really have the knowledge of our audience here today, so I kind of prepared a mix. So some high level concept, and then some deep. I don't know how many people find which part more useful for them. So it'll be interesting to know that. But if I know the audience, I will cater to their level, their needs. So for example, my classes last year, I try not to talk too much in one class. So I would break it down into one topic at a time. And yeah, it would be to really gauge who your audience are and be able to provide the right materials for them. It doesn't matter if, I think having people understand is more important than showing how much you know. So yeah, and there are a lot of academic talks that are very, very cutting edge, but if it's not given to the right audience, then people are not getting much out of it. That would be my effective technique.
Sounds good, Kitty. I'm wondering, I want to take you through a lightning round, which always allows us to learn more about our speakers. It's a fun thing that we usually do with our speakers to end this meeting. But before we go there, perhaps I'll ask about, I think there was an earlier question about whether you will be generous enough to share these slides that you used for this presentation with us.
Yeah, I would save it and email to you. And if
Sounds
people
good.
want to keep in touch, you can add me on LinkedIn.
Sure.
Yeah.
That sounds good.
That would be
then I was also going to ask about, I'm just wondering how does your typical day looks like at Microsoft as a senior program manager? I'm just wondering.
It can vary. It depends on the project I focus on. There are usually multiple projects in parallel that I need to overlook. So program management requires a lot of coordination between different teams and different people. So many meetings and communications, but I also have focus time that I will prepare documentation to present. Because now that most people are working remote, we have to have effective ways to communicate. So I think giving classes like this is actually one of the things that's helpful in that regard, is to prepare and visualization and summary that we can share with people around the world.
Sounds good. And how has being somebody who has got this flair for art made your work easier in any way, or your perspectives?
Sorry?
As your involvement in art or your a love for art made you, in what way has that made you stand out in your work and in quantum in general?
Yeah, actually, it is being very helpful for the team too. I developed these learning materials, and that's right at the front end for learners. They need to understand the content. They need to have way to visualize things. So the learning materials that I develop utilize a lot of my drawings, and the website that I develop is also very visual, so it's interactive. So it leverage. I also have user experience background. I've done many user experience projects and developing products. So those are interdisciplinary applications of different skills. Is also helpful for within the team writing documentation and drawing graphics to illustrate, say, our algorithm or hardware. Using visual has been very effective.
Sounds good. Thank you very much. Perhaps one last one from Nana. Can quantum computing help me if I want to be an aerospace engineer?
I would say definitely. I think quantum computing can be helpful for many, many different STEM areas. People who do aerospace also have all kinds of background and skills. And there are also quantum computing application in aerospace engineering. And I'm not in this area, so I can't give very specific examples, but I definitely see future jobs being very interdisciplinary. And quantum computing will be a core infrastructure for humanity. So I wouldn't be surprised if we would need to apply quantum algorithms or quantum methods in your areas of work. So aerospace engineering is by itself also very broad. So we have to
For sure.
Yeah.
For sure. Anyway, let's go through the lightning round and just have fun and see perhaps some of you learn a little bit more about you. So what is the biggest misconception about quantum technologies right now? As you know, what do you come across as the biggest misconception about quantum tech at the moment?
I think most people still don't understand the basic concepts. And last year, 2020, I think is a year of debunking a lot of hypes. There are a lot of hypes about quantum computing as if it could replace everything that we do using classical computing and it could be faster and better in every way. I think that might be a big misconception in the public. And the other thing is a lot of people may consider it a consumer area. They think that they can immediately, okay, so most people don't really care. They only care when they can have a quantum computer themselves, but that's not gonna happen, right? In the near future. It's going to be used in industry, in specific industries and application areas that can benefit from very specific applications of quantum computing. Optimization is right now being used broadly. It's not strictly what we talked about using those quantum algorithms. Optimization, quantum inspired is an area people get inspired using certain quantum mechanical methods in classical algorithms. I think there's just a lot of gap between where the industry is at and people's understanding overall. So I definitely hope that this kind of broader talks can help demystify some of the hypes and misconceptions.
Okay, thank you very much. What book are you currently reading outside quantum?
I'm reading a biography of philosopher Denis Diderot. He is the one who wrote the encyclopedia. He's a very interesting person and an early atheist and very visionary and independent thinker. Yeah.
Okay, sounds exciting. I should check that out as well. What is your favorite symbol or not so symbol, tool or a hack that you think is underappreciated?
Can you repeat that?
What is your favorite symbol? It could be simple, it could be something not so simple.
Symbol.
A hack, yeah, some technology that you are relying on that people may underappreciate.
I've never thought about that.
Anyway, what technology are you currently relying on that it makes your life so easy that you feel everybody else would figure it out?
Computer.
A classical one.
I do, yeah, most
one.
of my work, even my art, on the computer. So we rely on the software, that creative software that support artists to do digital work. And I'm also developing some of those in my other projects.
So it means you've got that big screen, the Microsoft Visual Studio that I've seen somewhere.
Oh, you mean Surface?
Yeah, Surface Studio.
Yeah, I don't have
yes.
one, unfortunately. I wish I have one.
That's okay, Kitty. So what is the best career advice you can offer to young people today?
Oh, I don't know. pursue your passion. Yeah, okay. Follow your heart.
Sounds good.
That's one of the best advice I got when I was younger.
sounds good. Any favorite getaway place that you may want to share with us?
Well, I'm very happy that we got to meet today, and really honored to be speaking here with you. So thank you everyone for attending.
Okay, I still have another one though.
Yeah.
So if you had a capable quantum computer today, what problem would you use it to solve?
Well, there's so many problems that we can use this to solve if we had the capability. Most difficult ones like climate change and drug simulation and fertilizer simulation, all the big global problems that we don't have very good solutions for. And one of the things that I work on, which is not yet utilizing quantum computing, and I think it's gonna still have a far way to go to even use quantum computing for, is to reduce the waste and pollution caused by the fashion industry right now, because the industry has been generating 10% of carbon footprint and is an industry built on mass production, and goods are overproduced. 30% of clothing ever made are never sold. Every year, the industry generates so much waste, tons and tons of waste sent into landfill and incinerators. I am working on a solution that will reduce that, but it's not using quantum computing yet. Maybe at some point in the future, but right now there are already things we can do using classical computing, using the cloud, that we can solve these problems. So we're building the next generation of computing, but we can already solve some biggest problems in the world using classical means.
Thank you very much, Kitty. Thanks so much for your time. Really appreciate it. Yeah, I think this is all we have for you, and we're really honored that you took time to be with us. We enjoyed having you, and we hope to connect with you in the future as well.
Thank you so much. Have a good day, everyone.